In this video, we're going to talk about symbol tables, an important data structure in many compilers. Before we talk about what a symbol table is, I want to talk about a generic algorithm that we're going to be seeing instances of over and over again for the rest of the course. So a lot of semantic analysis, and in fact a lot of code generation, can be expressed as a recursive descent of an abstract syntax tree. And the basic idea is that at each step we do the following three things. We're always processing a particular node in the tree. So if I draw a picture of the abstract syntax tree, we might have a node and some subtrees hanging off of it. And we may do some processing of the node before we do anything else. We arrive at the node, say, from the parent. We come into here from the parent. We do some processing of the node. And I'm just indicating that by coloring it blue to indicate that we did something here. And then we go off and we process the children. Okay? And after we process the children, after we come back to the node, we do something else. We may do some post-processing of the node, and then we return. And of course, at the same time, when we've got off and processed the children, we're processing all their nodes in the same pre and post fashion. So they're getting the same treatment with some stuff being done before each node is touched and some stuff being done after all their children have been processed. Okay? And there are many, many examples of this kind of an algorithm. This is called a recursive descent traversal of a tree. There are some instances in which we'll only process each node before we process the children, some where we only process each node after we process all the children, some where we do both, as illustrated here in this little diagram. And returning to the main topic of this particular video, when we're performing semantic analysis on a portion of the abstract syntax tree, we're going to need to know which identifiers are defined, which identifiers are in scope. An example of this kind of recursive descent strategy is how we can process let bindings to track the set of variables that are in scope. So we have our let node in the abstract syntax tree, and in one subtree we have the initialization, and in the other subtree we have E, the body of the let. All right? And then this is a let for some particular variable, and let's just write that variable inside the parent node here. And so when we begin processing of this node, let's imagine that we're coming from above. So we're doing this, we're processing the abstract syntax tree recursively, and so we reach this point from some parent, and there's going to be a set of symbols that are currently in scope. That's some data structure that lives off to the side. In fact, that's going to be our symbol table. And what is going to happen here? Well, the first thing we're going to have to do is we're going to have to process the initializer. We're going to need to know whether that's whatever function we're doing on this, like type checking or whatever. We might go down and process that first, and we'll pass the symbol table in. Okay, and then we're going to process the body of the let. But when we do that, we're going to pass in the set of symbols that are in scope, but also X is now going to be in scope. So X is going to be added before we process E to the set of symbols. And then when we return from the subexpression E, it's going to be removed. And so we'll restore the symbol table to its previous state so that after we leave this subtree of the abstract syntax tree, we only have the same set of symbols defined that we had before we entered it. So in the terminology of the three-part algorithm for a recursive descent that we had on the first slide, what are we doing here? Well, before we process E, we're going to add the definition of X to our list of current definitions, overriding any other definition of X that might have been visible outside of the let expression. Then we're going to recurse. We're going to process all of the abstract syntax tree nodes in the body of the let inside of E. And after we finish processing E, we're going to remove the definition of X and restore whatever old definition of X we had. And a symbol table is just a data structure that accomplishes these things. It tracks the current bindings of identifiers at each point in the abstract syntax tree. For a very simple symbol table, we could just use a stack, and it would have just, say, the following three operations. We can add a symbol to the symbol table, and that will just push the symbol, push the variable onto the stack and whatever other information we want, like its type. We'll have a find symbol operation that will look up the current definition for a symbol, and that can be done simply by searching the stack, starting from the top, for the first occurrence of the variable name. And this will automatically take care of the hiding of old definitions. So for example, if we have a stack that say has X, Y, and Z on it, and then we come into a scope that introduces a new Y, we would push Y on top, and now if we search through the stack, we would find this Y first, that effectively hiding the old definition of Y. And then when we leave a scope, we can remove a symbol simply by popping the stack. We'll just pop the current variable off of the stack. That will get rid of the most recent definition, and leave the stack, leave the set of definitions in the same state it was before we entered the node at all. So in this example, if we left the scope where the outer Y was defined and that was popped off the stack, so that was gone, now when we search for Y, we'll find the outer definition, the one that was defined outside of that inner scope. So this simple symbol table works well for let because the symbols are added one at a time and because declarations are perfectly nested. And in fact, the fact that declarations are perfectly nested is really the whole reason that we can use a stack. So take a look at this little example. Let's say we have 3 nested lets, and here I'm not showing the initializers in the left subtrees. They don't matter for what I want to illustrate. So if you think about it, as we walk from the root here down to the inner bindings, and we're pushing things on the stack, we'll push things on the stack in the order X, Y, and then Z. And then as we leave, after we've processed this subtree, and we're leaving it, walking back out, we're going to encounter these let scopes in exactly the reverse order, and popping them off the stack is exactly the order in which we want to remove them, and that's why a stack works well. So this structure works fine for lets, but for some other constructs it's not quite as good as it could be. So for example, consider the following piece of code. Illegal piece of code, I should add. Let's say we're declaring a method and it has 2 arguments named X. Now that's not legal, but in order to detect that it's not legal, I mean, why is it not legal? It's not legal because they're both defined in the same scope. So functions or methods have the property that they introduce multiple names at once into the same scope, and it's not quite so easy to use a stack where we only add one thing at a time or one name at a time to model simultaneous definition in a scope. So this problem is easily solved with just a slightly fancier symbol table. Here is the revised interface now with 5 methods instead of 3. The biggest change is that we now have explicit enter and exit scope functions. And so these functions start a new nested scope and exit a current scope. And the way to think about this is that our new structure is a stack of scopes. So what is on the stack is an entire scope, and then in a scope are all the variables that are defined at the same level within that single scope. So just like before, we have a find symbol operation that will look up a variable name, and it will return the current definition or null if there is no definition in any scope that's currently available. We'll have an add symbol operation that adds a new symbol to the table, and it adds it in the current scope, so whatever scope is at the top of our scope stack. And then one more new operation, check scope, will return true if X is already defined in the current scope. So this, just to be clear on what this does, this returns true if X is defined in exactly the top scope. It doesn't return true unless X is defined in the scope at the very, very top of the stack, and this allows you to check for double definition. So for example, in the code that I had before on the previous slide, if we had 2 declarations of X, how would we check this? Well, we would add X to the symbol table in the current scope, and then we would ask, well, is X already defined in this scope for the second one? And this interface would return true, and we would know to raise an error saying that X had been multiply defined. Finally, let me just add that this is the symbol table interface, or something very close to this is the symbol table interface that is supplied with the Cool project, and there's already an implementation of this interface provided if you don't want to write your own. So let's wrap up this video by talking a little bit about class names, which behave quite differently from the variables introduced in let bindings and in function parameters. In particular, class names can be used before they are defined, as we discussed a few videos ago. And what that means is that we can't check class names in a single pass. We can't just walk over the program once and check whether every class that is used is defined, because we don't know that we've seen all the definitions of the classes until we reach the very end of the program. And so there is a solution to this. We have to make 2 passes over the program. In the first pass, we gather all the class definitions. We go through and we find every place where a class is defined. We record all of those names. And then in the second pass, we go through and look at the bodies of the classes and make sure they only use classes that were defined. And the lesson here, this is actually not complicated to implement. I think it's quite clear, or should be quite clear, how this will work. But the message here is that semantic analysis is going to require multiple passes, and probably more than 2. And in fact, you should not be afraid when structuring your compiler to add lots and lots of simple passes if that makes your life easier. So it's better to break something up into, say, 3 or 4 simple passes rather than to have one very, very complicated pass where all the code is entangled. I think you'll find it much easier to debug your compilers if you're willing to make multiple passes over the input.